The universe is vast, mysterious, and endlessly fascinating. But what if I told you that despite centuries of exploration and discovery, there are questions so profound that even our brightest minds are left without answers? Questions like what existed before the beginning of time? Or what lies beyond the edges of the cosmos we can see? As you look up at the night sky glittering with countless stars, have you ever felt the pull of the unknown, the urge to unravel the secrets hidden in the fabric of space itself? In today's journey, we're diving headfirst into the uncharted, exploring 30 of the most mind-boggling questions about space mysteries so deep they continue to stump scientists and ignite our imagination. From the enigmatic force that accelerates the universe's expansion to the secret lives of black holes, these questions don't just challenge our understanding, they remind us of just how much more there is to uncover. So fasten your seatbelt as we embark on a cosmic odyssey, venturing into the heart of the great unknown. By the end of this journey, you might find yourself looking at the universe and your place in it with entirely new eyes. Now turning to one of the most profound questions in cosmology, what existed before the Big Bang? Imagine a moment so elusive, so enigmatic, that it defies the very concept of time itself. The Big Bang is widely regarded as the beginning of our universe, a moment when space, time, matter, and energy burst into existence. But if time itself started with the Big Bang, can we even define what came before? Some scientists argue that asking what existed before the Big Bang is like asking what is north of the North Pole, an impossible question because the framework of time and space simply did not exist. However, others propose tantalizing theories. One possibility is the idea of a multiverse, where our universe is just one of many, constantly bubbling into and out of existence. Perhaps the Big Bang was merely the birth of our bubble, while countless others expanded and collapsed beyond our view. Another theory suggests the concept of a cyclical universe, where the cosmos undergoes endless cycles of expansion and contraction, with each Big Bang marking the start of a new era. And then there are quantum fluctuations, tiny, random disturbances in a vacuum that might have sparked the creation of all we see today. Yet despite these intriguing ideas, no definitive evidence exists to confirm what, if anything, came before. This question remains one of the greatest mysteries, leaving us to wonder if the answer lies forever beyond the horizon of human comprehension. Moving forward, we encounter an equally enigmatic force that shapes the very structure of the cosmos. What is dark energy? Moving forward, we delve into one of the most perplexing mysteries of modern astronomy. What is dark energy? Imagine an invisible force working silently yet relentlessly to reshape the cosmos. This enigmatic phenomenon is believed to be the driving power behind the accelerating expansion of the universe. But what exactly is it, and why does it remain so elusive? Dark energy makes up an astonishing 68% of the universe, dwarfing everything else we know, including stars, planets, and even dark matter. Despite its overwhelming presence, scientists have yet to directly detect or identify what it truly is. Some theories suggest it could be a property of space itself, a kind of energy inherent in the very fabric of the cosmos. Others propose that it might be a dynamic field that evolves over time, subtly influencing the growth of the universe. What complicates the mystery further is how dark energy seems to oppose gravity, pushing galaxies apart at an ever-increasing rate. This raises profound questions about the ultimate fate of the universe. Will it expand forever, leading to a cold, desolate Big Freeze? Or could dark energy grow stronger over time, tearing apart galaxies, stars, and even atoms in a dramatic Big Rip? Ultimately, the nature of dark energy challenges the very limits of human understanding, leaving us with more questions than answers. And as we seek to unlock its secrets, another cosmic enigma looms on the horizon. What is dark matter? Now turning to another baffling mystery of the cosmos, what is dark matter? Accounting for approximately 27% of the universe, dark matter is a substance we cannot see, touch, or directly detect, yet its presence is known through its gravitational influence. Without dark matter, galaxies as we know them could not exist. It acts as the invisible glue that binds galaxies together, preventing them from flying apart as they spin. But what exactly is it? Scientists have proposed a range of possibilities, from exotic particles not yet discovered to massive compact objects hidden in the depths of space. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, which is why it remains effectively invisible to even the most sophisticated telescopes. Instead, its existence is inferred through its effect on visible matter like stars and galaxies, as well as its influence on the bending of light, a phenomenon called gravitational lensing. Despite decades of research and countless experiments, no one has been able to capture or directly measure dark matter. This has led to theories that challenge the very foundations of physics, suggesting that our understanding of gravity itself may need to be redefined. The hunt for dark matter continues with ever more sensitive detectors and experiments pushing the boundaries of our knowledge. Could it be that dark matter holds secrets to the origins of the universe, or perhaps even clues to dimensions beyond our own? While we search for answers to these monumental questions, let us journey deeper into another profound unknown. Are we truly alone in the universe? Moving forward, we arrive at one of the most profound questions humanity has ever asked. Are we alone in the universe? For centuries, we have gazed at the night sky, wondering if another civilization might be looking back. The quest to answer this question has taken us to the boundaries of science and imagination. Scientists have been scanning the cosmos for radio signals, carefully listening for whispers from an intelligent civilization. Projects like the search for extraterrestrial intelligence have devoted years to analyzing signals from deep space, hoping to detect patterns that could signify communication from advanced beings. Beyond listening, we are also searching visually. With powerful telescopes, researchers have identified thousands of exoplanets, planets orbiting stars outside our solar system, many of which lie in the so-called habitable zone, where conditions might support liquid water and, by extension, life as we know it. Astrobiology, the study of life in the universe, combines findings from biology, chemistry, and planetary science to explore how life might arise and thrive beyond Earth. However, despite all our efforts, the universe has remained eerily silent. This brings us to the heart of the enigma, the Fermi paradox. If the universe is so vast and so old, and if intelligent life is abundant, why have we not yet encountered clear evidence of its existence? One possible explanation is that intelligent civilizations might be so far apart in distance or time that they never overlap. Another theory suggests that civilizations destroy themselves before they can reach the technological capability to communicate or travel between stars. The Drake equation, another tool to explore this puzzle, estimates the number of advanced civilizations in the galaxy by factoring in variables like the rate of star formation, the number of planets that could support life, and the likelihood of life developing intelligence. Yet, even with optimistic assumptions, the equation leaves us with more questions than answers. Could it be that life is far rarer than we imagine, or is it simply hiding in forms we cannot yet detect or understand? As we continue our search, from sending probes to distant worlds to studying the atmospheres of exoplanets for signs of life, this question challenges the limits of our technology, our understanding, and even our imagination. While the mystery deepens, let us turn our gaze toward another cosmic marvel. What happens in the heart of a black hole? Moving forward, we venture into one of the most mind-bending enigmas of modern physics. What happens in a black hole? A black hole is a region in space where gravity is so strong that nothing, not even light, can escape its pull once it crosses a boundary called the event horizon. This immense gravitational force warps space and time to such an extreme that the usual rules of physics seem to break down. At the center lies the singularity, a point of infinite density where the known laws of physics simply cease to function. But what truly happens to anything that falls into this cosmic abyss? Does matter get obliterated, transformed, or transported somewhere we cannot comprehend? Some theories suggest that the intense gravity compresses matter into an unimaginably small point, essentially erasing its physical structure. Yet, this idea conflicts with a fundamental principle of physics, the conservation of information, which states that information cannot be destroyed. This paradox has led scientists to speculate about alternative possibilities. Could black holes act as portals to other regions of the universe or even alternate universes entirely? Wormholes, hypothetical tunnels through space and time, could theoretically exist within a black hole, providing a shortcut to distant parts of the cosmos. While such ideas remain speculative and unproven, they push the boundaries of our understanding of space, time, and reality itself. Recent research into phenomena like Hawking radiation, a form of energy theorized to be emitted by black holes, offers some clues, but many questions persist. Do black holes eventually evaporate over time, releasing their contents back into the universe in some form? Or does the information they consume remain locked away forever? As we continue to study these mysterious objects through observations and simulations, black holes challenge not only our understanding of physics, but also our imagination. With this cosmic conundrum in mind, let us explore yet another profound question. What is the ultimate fate of the universe? With the next phase of the journey in sight, we turn our gaze to the ultimate destiny of the universe, a question as vast and enigmatic as the cosmos itself. What will happen to everything, every planet, star, galaxy, and particle in the distant future? Scientists have proposed several theories, each as fascinating as it is unsettling. One possibility is the Big Crunch, where the universe's expansion eventually reverses due to gravitational forces. In this scenario, galaxies would cease moving apart and begin collapsing inward, culminating in an unimaginably hot, dense state similar to the conditions of the Big Bang. Alternatively, there is the theory of the Big Freeze. Here, dark energy, a mysterious force causing the universe to expand at an accelerating rate, continues its relentless push, spreading matter so thin that stars burn out, galaxies grow dim, and the cosmos becomes a cold, dark, and silent void. The third scenario, the Big Rip, takes this expansion to an even more extreme outcome. In this case, dark energy's influence grows so overpowering that it eventually tears apart not just galaxies and stars, but even atoms and the fundamental fabric of space-time itself. What determines which of these fates awaits us? It all hinges on the universe's density and the nature of dark energy, the very components that remain some of the greatest mysteries in cosmology. Observation of the cosmic microwave background, the faint afterglow of the Big Bang, and measurements of the universe's accelerating expansion provide us with tantalizing clues, yet we are far from definitive answers. Each theory, whether it predicts an intense collapse, eternal cold, or catastrophic disintegration, invites us to confront the profound impermanence of everything we know. As we ponder these scenarios, we must ask ourselves, will humanity ever unlock the secrets of the cosmos in time to understand our place in its grand story? With this humbling mystery in mind, let us press on to explore another puzzling question. Why does time only move forward? Now turning to the intriguing enigma of time itself, we ask, why does time only move forward? This forward flow, often called the arrow of time, is something we experience every day, yet its deeper cause remains a puzzle. The key to understanding this lies in a concept called entropy, which is a measure of disorder or randomness in a system. According to the second law of thermodynamics, entropy in a closed system tends to increase over time. Simply put, the universe naturally moves from order to disorder. For instance, a cup of hot coffee left on a table will gradually cool down as heat spreads to the surrounding air. The process is irreversible. The coffee won't spontaneously heat back up on its own. This increase in entropy creates the appearance of time moving forward. But here's the twist: many fundamental laws of physics do not actually require time to flow in one direction. They work just as well if time were to move backward. This contradiction leaves scientists wondering if the arrow of time is simply a byproduct of the universe's initial conditions after the Big Bang, where it started in an extremely low entropy state and has been increasing ever since. It also raises profound questions about the nature of time itself. Why does our perception of time align so closely with this increase in entropy? Could it be that our experience of time is connected to how we process information or make sense of cause and effect? And if entropy defines the flow of time, could there be regions in the universe where time flows differently or even backward? These are the kinds of questions that keep physicists awake at night, pushing the boundaries of what we know about the cosmos. As we move forward, let us peer deeper into the distant reaches of the universe to uncover the mysteries of quasars and their dazzling secrets. Now turning to one of the brightest phenomena in the universe, we ask, what are quasars really? Quasars are extraordinary objects found at the centers of distant galaxies, and their brilliance is so intense that they can outshine entire galaxies containing billions of stars. But what makes them shine so brightly? The answer lies in the colossal supermassive black holes at their cores. These black holes, millions or even billions of times the mass of our Sun, are surrounded by a swirling disk of gas and dust called an accretion disk. As material spirals toward the black hole, immense gravitational forces generate staggering amounts of energy. This energy is released in the form of light, heat, and radiation, creating the dazzling glow of a quasar. What's even more fascinating is that quasars are like cosmic lighthouses from the early universe. Many of them are located billions of light years away, meaning the light we see from them has traveled across space for billions of years. This makes quasars invaluable to astronomers because they offer a glimpse into the universe's distant past, helping us understand what conditions were like shortly after the Big Bang. By studying quasars, scientists can learn about the formation and evolution of galaxies, the behavior of supermassive black holes, and even the distribution of matter in the early cosmos. Yet, questions remain. Why are quasars so much more common in the distant past than in the present-day universe? Could it be that they represent a phase of galaxy growth that most galaxies, including our own Milky Way, experienced long ago? And what triggers a quasar to form in the first place? These are mysteries that continue to drive astronomical research forward. With the light of quasars illuminating the early universe, let us now turn our gaze to the very edges of the cosmos to explore what lies beyond the limits of the observable universe. With the next phase of the journey in sight, we arrive at an even more perplexing question. What lies at the edge of the universe? To understand this, we first need to grasp the concept of the observable universe. The observable universe is the portion of the cosmos that we can see, determined by the speed of light and the age of the universe itself, which is around 13.8 billion years. Light from objects farther away simply hasn't had enough time to reach us, meaning our view is limited by this so-called cosmic horizon. But what happens beyond this horizon? Is there more universe out there, or does it simply end? One idea suggests that the universe might be infinite, stretching endlessly beyond our observational limits. In this case, the edge we perceive is merely a boundary of what we can detect, not the actual edge of existence. Another possibility points to the multiverse theory, which speculates that beyond the observable cosmos might exist other universes entirely, each with different physical laws, dimensions, and realities. Then there's the notion of a cosmic void, a concept where the universe beyond our horizon could be sparsely populated with matter or perhaps even completely empty, leaving an unending expanse of nothingness. Adding to the mystery, scientists wonder whether the universe has a shape or structure that might influence what's beyond. Could it be curved like a giant sphere, folded like a complex tapestry, or flat and infinite? The true answers remain elusive, as our current technology and understanding of physics can only take us so far. For now, we are left to dream and theorize about what might lie beyond that distant, unreachable boundary. As we ponder the tantalizing edge of the universe, our next question invites us to contemplate something even deeper. Why does the universe exist at all? As the next challenge unfolds, we find ourselves facing one of the most profound questions of all. Why does the universe exist? This is a mystery that transcends the boundaries of science, philosophy, and even human imagination. From a scientific perspective, some theories suggest that the universe may have arisen from quantum fluctuations in a vacuum. These fluctuations are temporary changes in energy that occur even in empty space, potentially giving rise to particles and, under the right conditions, leading to the creation of everything we see today. But why would these fluctuations happen in the first place, and what triggered them? For some, this leads to the anthropic principle, which posits that the universe must have the properties necessary to support life because, quite simply, we are here to observe it. In essence, the conditions of the universe might not be special at all. They might just be one possibility among many, and we happen to exist in the one where life is possible. Still, others look toward philosophical or metaphysical explanations. The idea that something rather than nothing exists is a question that may never have a definitive answer. Could existence itself be a fundamental state, one that simply is and always has been without a need for a cause? Or is our universe part of a grander framework, such as the multiverse, where countless other universes exist with their own unique rules and realities? These concepts challenge our understanding of causality and existence, leaving us grappling with what it means to exist at all. Perhaps the ultimate answer lies in realms we cannot yet comprehend, or maybe the question itself is beyond the limits of human reasoning. For now, it remains one of the greatest enigmas of all time, urging us to keep questioning, exploring, and seeking understanding. Speaking of mysteries, let's shift our focus to the origins of life as we explore the next question: how did life begin on Earth? Now turning to the next profound question, how did life begin on Earth? This puzzle has intrigued scientists and philosophers alike for centuries, and while we have made progress in understanding the conditions necessary for life, the ultimate origin remains shrouded in mystery. One intriguing possibility is that life's building blocks, organic molecules like amino acids and nucleotides, were not formed solely on Earth. Instead, they may have come from afar, hitching a ride on comets or asteroids that bombarded the early Earth. This idea, known as panspermia, suggests that the seeds of life could be scattered across the universe, carried by celestial objects. Could these ingredients have been delivered to Earth from the far reaches of space, sparking the incredible diversity of life we see today? Another theory points to hydrothermal vents deep beneath the ocean's surface. These underwater geysers release heat and minerals, creating an environment ripe for chemical reactions. Could these extreme conditions have provided the perfect cradle for life to emerge? Or perhaps life originated from a primordial soup of organic compounds on the Earth's surface, where lightning, ultraviolet light, or volcanic activity may have provided the energy needed for simple molecules to evolve into complex ones. The idea that life's recipe might be universal opens up exciting possibilities for finding life beyond Earth. If organic molecules can form in the vastness of interstellar clouds, as some researchers believe, then the ingredients for life might be scattered throughout the cosmos. This raises a tantalizing question. Could similar processes have taken place on other planets or moons, leading to extraterrestrial life in some form? While we may one day replicate the conditions of life's origin in a laboratory, many questions remain. Were we a cosmic accident, or is life an inevitable consequence of the universe's laws? Each theory, from panspermia to hydrothermal vents, brings us closer to understanding this incredible mystery, yet the full story eludes us. For now, the origin of life remains one of science's most compelling enigmas, urging us to explore further. And speaking of mysteries tied to space, let's now venture into the realm of interstellar signals as we tackle the next perplexing question: what are fast radio bursts? Now turning to the fascinating phenomenon of fast radio bursts, these enigmatic and fleeting flashes of radio waves from distant galaxies are among the most mysterious events in astronomy. Lasting only milliseconds, fast radio bursts release an extraordinary amount of energy, more than what our sun emits in a day, all packed into this brief moment. But what causes them? That is the million-dollar question puzzling scientists worldwide. One leading hypothesis attributes fast radio bursts to the collision of neutron stars, the dense remnants of dead stars that can unleash immense energy when they merge. However, this theory cannot explain all fast radio bursts, especially those that repeat, sometimes sporadically, with no discernible pattern. Other possibilities include magnetars, which are neutron stars with incredibly powerful magnetic fields. These cosmic powerhouses are known for their intense bursts of energy and might produce fast radio bursts through violent magnetic activity. Yet, even this explanation doesn't cover every observed fast radio burst, leaving researchers scratching their heads. Here's where things get even more intriguing. Some scientists have speculated that fast radio bursts could be artificial in origin. Could they be signals from advanced alien civilizations attempting to communicate across the vast expanse of space? It's a possibility that cannot be completely dismissed, though no concrete evidence supports this idea so far. Adding to the mystery is the sheer number of these bursts. With improved telescopes and detection methods, astronomers now realize that fast radio bursts are not rare. They could be occurring thousands of times a day across the universe. What cosmic mechanism could produce such a prolific phenomenon? Despite the advancements in understanding, each new discovery about fast radio bursts raises more questions than answers. Are they the echoes of cataclysmic cosmic events, or do they hint at something even stranger, something we have yet to imagine? Until we unravel their true origin, fast radio bursts remain a captivating puzzle, challenging the limits of our knowledge. Speaking of cosmic enigmas, let's turn to another extraordinary mystery. What exactly are neutron stars? Now turning to one of the most extreme objects in the universe, neutron stars are the astonishing remnants of massive stars that have ended their lives in spectacular supernova explosions. When these stars exhaust their nuclear fuel, their cores collapse under the overwhelming force of gravity, compressing their mass into an object no larger than a city, but with a density so immense that a single teaspoon of neutron star material would weigh as much as a mountain. These cosmic titans are held together by gravity so strong that it overwhelms the usual repulsion between atomic nuclei, leaving behind a dense sphere composed almost entirely of neutrons, hence their name. But their incredible density is just the beginning of their mysteries. Neutron stars are also known for their mind-boggling magnetic fields, which can be billions or even trillions of times stronger than Earth's magnetic field. These magnetic properties give rise to some of the most fascinating phenomena in the cosmos. For instance, certain neutron stars emit steady pulses of radio waves or light, creating a cosmic lighthouse effect. These are known as pulsars, and they are some of the most precise timekeepers in the universe, with their pulses occurring at perfectly regular intervals. Scientists believe this happens because the neutron star's magnetic field funnels charged particles along its poles, creating beams of radiation that sweep across space as the star rotates. But why are these beams so consistent, and what governs their behavior? That remains a captivating question. Adding to the enigma, neutron stars are not a uniform group. Some are magnetars, neutron stars with outrageously strong magnetic fields, capable of releasing bursts of energy so intense they can disrupt satellites even from thousands of light years away. Yet, the formation and life cycles of these magnetars are still not fully understood. Additionally, some neutron stars exhibit behaviors we cannot yet explain, such as sudden changes in their rotational speed, known as starquakes, which hint at complex interior structures that defy our current knowledge of physics. Neutron stars also raise questions about their ultimate fates. Do they remain as they are, or can they transform into something even stranger, such as a black hole, if they accumulate enough mass? And could their interactions with other cosmic objects, such as companion stars, lead to phenomena we have not yet observed? Every neutron star is a frozen snapshot of an incredibly violent process, and studying them not only uncovers the life cycles of stars, but also pushes the boundaries of physics itself. As we marvel at the dense, fascinating world of neutron stars, another cosmic question looms just as intriguingly. Is it possible to travel faster than light? Moving forward, let us consider one of the most captivating and debated questions in modern physics. Can we travel faster than light? According to Einstein's theory of relativity, the speed of light is the ultimate cosmic speed limit, a barrier that nothing with mass can surpass. The reason lies in the nature of space, time, and energy. As an object approaches the speed of light, its mass effectively increases, requiring more and more energy to accelerate further. At the speed of light itself, the energy requirement becomes infinite, rendering faster than light travel impossible within the framework of our current understanding of physics. But does this mean the dream of interstellar or even intergalactic travel is destined to remain just that, a dream? Not necessarily. Scientists and thinkers have explored fascinating concepts that could, in theory, bypass this cosmic speed limit without violating the laws of physics. One idea is the concept of a warp drive, a theoretical propulsion system that could distort the fabric of space-time itself. Instead of moving a spacecraft faster than light through space, a warp drive would contract space in front of the ship and expand it behind, effectively moving the spacecraft through a warp bubble. This ingenious idea, inspired by solutions to Einstein's equations, would allow the ship to reach distant locations without technically breaking the speed of light barrier. However, the energy requirements for such a feat are astronomical and far beyond our current technological capabilities. Some calculations even suggest that the energy needed would exceed the total energy output of the observable universe, though more recent studies propose ways to reduce this requirement. Another intriguing concept involves wormholes, hypothetical shortcuts through space-time that could connect two distant points instantly. Imagine folding a piece of paper in half so that 2 points touch, then poking a hole through them. This is the basic idea behind wormholes, a bridge through space and time. While wormholes emerge as solutions in the equations of general relativity, their existence is purely theoretical. If they do exist, they might be incredibly unstable, collapsing before anything could pass through. Or they might require exotic matter with negative energy to stabilize them, something we have not yet discovered. And even if wormholes were possible, there is no guarantee they could be traversed safely or lead to the destinations we might hope for. Beyond these two concepts, there are other speculative ideas, such as using tachyons, hypothetical particles that always move faster than light, or employing quantum phenomena to teleport information instantaneously. However, these ideas remain in the realm of theoretical physics, with little evidence to suggest they could ever become practical methods of travel. Despite the immense challenges, the question of faster-than-light travel continues to inspire physicists and engineers. It pushes the boundaries of our understanding and fuels innovations that could one day bring us closer to the stars. For now, the speed of light remains an unbroken barrier. But as history has shown, scientific barriers often yield to human ingenuity and perseverance. As we ponder the vastness of the cosmos and our place within it, let us shift our gaze back to our own solar system to explore one of its most enduring mysteries, the origin of our moon. Now turning to the next chapter of cosmic inquiry, what exactly created the moon? Our closest celestial neighbor has been a constant in the night sky, inspiring myths, guiding tides, and serving as a silent witness to Earth's history. But its origins remain a topic of scientific investigation and debate. The leading theory, known as the giant impact hypothesis, suggests that over 4 billion years ago, a Mars-sized object, often referred to as Theia, collided with the young Earth. The immense force of this collision ejected a significant amount of debris into orbit around our planet, which eventually coalesced to form the Moon. This theory helps explain many aspects of the Moon's structure, such as its size and its relative lack of iron compared to Earth. However, mysteries still linger. For instance, if the Moon was primarily formed from the remnants of Theia, why does its composition so closely resemble Earth's crust? Studies of lunar rocks brought back by the Apollo missions reveal striking similarities in isotopic ratios, suggesting the Moon and Earth share a common origin. Yet they are not entirely identical. Subtle differences exist, and these discrepancies raise questions about the specifics of the impact and whether our understanding of planetary formation is complete. Some scientists propose variations of the giant impact hypothesis, such as multiple smaller impacts or a high-energy collision that thoroughly mixed the materials of Earth and Theia before the Moon formed. Others suggest alternative explanations, like the Moon forming alongside Earth from the same primordial disk of material, or even being captured by Earth's gravity after forming elsewhere in the solar system, though these ideas face significant challenges in explaining the observed evidence. Understanding the Moon's origin is not just about solving a fascinating puzzle. It sheds light on the formation of other moons, planets, and even entire solar systems. By studying our Moon, we gain insights into the chaotic processes that shaped the early solar system and set the stage for the emergence of life on Earth. With so much still unknown, the Moon remains a compelling subject of exploration, both scientifically and philosophically. And speaking of mysteries within our solar system, let us next consider whether there might be a hidden ninth planet lurking in its farthest reaches. Moving forward, let us venture into the enigmatic outskirts of our solar system to tackle another provocative question. Is there a ninth planet hidden in the shadows beyond Neptune? For years, astronomers have speculated about the existence of a massive, unseen world, often referred to as Planet 9 or Planet X, that might haunt this distant realm. The idea gained traction when researchers observed peculiar clustering in the orbits of certain Kuiper belt objects, which are icy bodies located far beyond Neptune. These objects seem to follow paths that can only be explained by the gravitational influence of a large, unseen planet. Could we be looking at evidence of a giant, yet undiscovered neighbor exerting its dominance on the distant fringes of our solar system? Theoretical models suggest that if Planet 9 exists, it would likely be several times the size of Earth, orbiting the Sun at a staggering distance that could be up to hundreds of times farther away than Earth's orbit. Such a remote location would make the planet incredibly faint and difficult to spot with even the most advanced telescopes. But even without direct observation, the gravitational fingerprints it may leave on nearby objects have led some scientists to estimate its orbit, mass, and even composition. These clues paint a picture of a mysterious ice giant, potentially similar to Uranus or Neptune, wandering in the dark, frigid outskirts of our solar system. Despite the intrigue, the search for Planet 9 remains elusive. Some astronomers question whether the unusual orbits of Kuiper belt objects might be explained by interactions with smaller celestial bodies or other, yet unknown forces. Others argue that the evidence is compelling enough to justify dedicated searches, which are actively underway. Advanced telescopes and sky surveys in the coming years may finally provide answers or raise even more questions. If Planet 9 is eventually discovered, it will not only redefine our understanding of the solar system's architecture, but also challenge existing theories about how planetary systems form and evolve. The possibility of a hidden world lurking silently in the cold outer reaches reminds us that even in our own cosmic backyard, there are still profound mysteries waiting to be uncovered. And speaking of celestial enigmas, let us now unravel the incredible power and mystery of gamma-ray bursts, some of the most energetic phenomena in the universe. Now turning to the next cosmic mystery, let us uncover the astonishing phenomenon of gamma-ray bursts. These are brief, yet unimaginably powerful explosions of energy that can release more radiation in a few seconds than our Sun will emit over its entire lifetime. Gamma-ray bursts are so intense that they can outshine entire galaxies during their fleeting existence. But what causes these incredible outbursts, and why are they so immensely energetic? Scientists believe there are two primary types of gamma-ray bursts. The first, known as long-duration bursts, are thought to emanate from the collapse of massive stars in distant galaxies. When such a star exhausts its nuclear fuel, its core collapses into a black hole or neutron star, releasing an immense amount of energy as its outer layers are blasted off into space. This process, often associated with a supernova, births some of the most dazzling yet chaotic displays in the cosmos. The second type, short-duration bursts, are believed to arise from the collision of two neutron stars or a neutron star and a black hole. These cataclysmic events compress matter into super-dense states, unleashing enormous gravitational forces and creating these powerful jets of high-energy gamma rays. Yet, despite our growing understanding of their origins, many questions remain unanswered. For instance, why do gamma-ray bursts vary so widely in duration and intensity? Some last only milliseconds, while others can stretch to several minutes. What factors dictate the precise mechanics of their formation, or how the energy is distributed in such a focused and narrow beam? These bursts are so distant and brief that observing them in real time poses a monumental challenge to astronomers. Moreover, the astonishing energy released by gamma-ray bursts raises fundamental questions about the ultimate limits of astrophysical processes. How does the universe manage to concentrate such immense power into such a confined space and time? What we do know is that gamma-ray bursts are not only a spectacle but also a window into the extreme physics of the universe. By studying them, scientists hope to uncover clues about the early stages of star formation, the behavior of matter under extreme conditions, and even the evolution of the cosmos. With advancements in satellite technology and ground-based observations, astronomers are beginning to piece together the puzzle, but for every answer, new questions seem to emerge. And on that note, as we traverse further into the depths of cosmic enigmas, let us delve into another puzzling entity, the Great Attractor, a gravitational anomaly influencing our very galaxy's motion. Now turning to the Great Attractor, we encounter one of the most perplexing mysteries in astronomy. This enigmatic region of space exerts a powerful gravitational pull on everything around it, including our very own galaxy, the Milky Way. Imagine billions of galaxies spanning hundreds of millions of light years, all moving in one general direction at staggering speeds. This collective motion, known as the cosmic flow, points toward a poorly understood region named the Great Attractor. But what exactly is it, and why does it hold such sway over the universe? The Great Attractor lies roughly 200 million light-years away in the direction of the constellation Centaurus. However, much of it remains hidden behind what astronomers call the zone of avoidance, a densely crowded region of stars, gas, and dust in our galaxy that obscures our view. Despite decades of research, its true nature remains cloaked in mystery. Is it a colossal structure of dark matter, an accumulation of massive galaxy clusters, or something else entirely? What we do know is that its gravitational influence is immense. It pulls galaxies in its vicinity with such strength that it disrupts the uniform expansion of the universe in this region. Scientists estimate that the Great Attractor has the mass equivalent to tens of thousands of galaxies. But where is all this mass? Why can't we see it? Some theories suggest that much of this mass could be in the form of dark matter, the invisible and mysterious substance that makes up a significant portion of the universe. Another uncertainty lies in trying to pinpoint the exact boundaries of the Great Attractor. Observations from X-ray telescopes have revealed dense clusters of galaxies in its vicinity, such as the Norma cluster, which are part of the larger Laniakea supercluster, a vast cosmic structure of which the Milky Way is also a member. Could these clusters collectively form the Great Attractor, or is it just a piece of something even larger and more complex? What intrigues scientists even further is the possibility that the Great Attractor might just be one node in an intricate web of even larger cosmic structures. Beyond it lies the Shapley supercluster, an even more massive region of galaxies, suggesting that the Great Attractor might itself be getting pulled towards something even bigger. The Great Attractor challenges our understanding of gravity, cosmic structures, and the unseen forces shaping the universe. Studying it may eventually illuminate the hidden framework of the cosmos, helping us understand how galaxies, clusters, and superclusters are interconnected. But for now, it remains an elusive puzzle shrouded in mystery and wonder. With that, we move further into the depths of the unknown as we explore the extreme and fascinating world of magnetars, one of the cosmos's most extraordinary phenomena. Moving forward, we encounter the extraordinary phenomenon of magnetars, some of the most mysterious and powerful objects in the cosmos. Magnetars are a rare type of neutron star, which are the remnants of massive stars that collapsed after exhausting their nuclear fuel. What sets magnetars apart from typical neutron stars is their mind-bogglingly strong magnetic fields, which are estimated to be trillions of times more intense than Earth's magnetic field. To put that into perspective, if a magnetar were located just 100,000 miles away, its magnetic force could erase the data on every credit card on Earth. What causes these magnetic fields to be so incomprehensibly strong? This remains one of the great mysteries of astrophysics. Scientists believe that it may have something to do with the rapid rotation and unique magnetic properties of the star during its formation. When a massive star collapses into a neutron star, its magnetic field can become drastically compressed, amplifying its intensity. However, why only a small fraction of neutron stars become magnetars is still an open question. Magnetars are also known for their dramatic and unpredictable behavior. Every so often, they release colossal amounts of energy in the form of what are called soft gamma repeaters. These are bursts of high-energy radiation so powerful that they can temporarily disrupt Earth's upper atmosphere from thousands of light years away. The source of these bursts is thought to be starquakes, essentially cracks in the rigid surface of the magnetar caused by the intense stresses of its magnetic field. Imagine an earthquake on a cosmic scale, sending shockwaves of energy across the universe. But the mysteries don't stop there. Magnetars typically have relatively short lifespans in cosmic terms, with their magnetic fields decaying over tens of thousands of years, an instant compared to the billions of years most stars exist. Why do they fade so quickly, and what happens to them afterward? Do they become ordinary neutron stars, or do they transform into something entirely different and unknown? Their rarity also adds to the enigma. Astronomers have only identified a few dozen magnetars in our galaxy, leaving us wondering how many might be hiding in the vast stretches of space we have yet to explore. Could their extreme properties offer clues to other cosmic phenomena we currently don't understand? Some scientists speculate that studying magnetars might even shed light on the elusive nature of dark matter or the behavior of gravity in extreme conditions. Magnetars remind us that even in a universe filled with marvels, there are still phenomena that defy our understanding and stretch the boundaries of what we think is possible. From their enigmatic formation to their spectacular outbursts, they remain a subject of intense fascination and study. As we continue to unravel their secrets, we are also uncovering more profound questions about the universe itself. With that, let's turn our attention to yet another captivating mystery, the breathtaking beauty and composition of Saturn's rings. Now turning to the awe-inspiring rings of Saturn, one of the most iconic and visually stunning features in our solar system. These rings, stretching hundreds of thousands of miles wide but astonishingly thin in proportion, are composed primarily of ice particles mixed with rocky debris and dust. The fragments range in size from tiny grains to chunks as large as houses, creating a shimmering, almost ethereal display when illuminated by the sun. But what makes these rings so fascinating is not just their beauty, but the mystery of their origin and age. Scientists have long debated how Saturn's rings came to be. One prevailing theory suggests that they might be the remnants of a moon that ventured too close to Saturn and was torn apart by the planet's immense gravitational forces in an event known as the Roche limit. Another possibility is that the rings are made up of material from the early solar system that never coalesced into a larger moon or body. If this is true, the rings could provide a rare glimpse into the primordial building blocks that formed not only Saturn but our entire solar system. The age of Saturn's rings is another puzzle that continues to baffle researchers. Some studies suggest that the rings are relatively young, perhaps only a few 100 million years old, a mere fraction of Saturn's over 4 billion years of existence. This hypothesis is supported by the rings' brightness, which indicates they haven't had enough time to accumulate significant cosmic dust and debris. However, other evidence hints that they could be as ancient as the planet itself, raising questions about how they have managed to remain so pristine over eons. Adding to the intrigue, the rings are not static. They are in constant motion, with the particles colliding, clumping together, and breaking apart in a delicate cosmic dance. Gravitational interactions with Saturn's moons, known as shepherd moons, also help to sculpt and maintain the distinct gaps and divisions within the rings. For instance, the famous Cassini division, a large gap between the O ring and the B ring, is shaped by these gravitational influences, creating one of the most recognizable features in the ring system. What will ultimately happen to these rings? Some predictions suggest that they are slowly disintegrating under the influence of Saturn's gravity and could disappear entirely in a few 100 million years. If so, we are living in a rare period of cosmic history when Saturn's rings are at their most vibrant and prominent. Imagine future generations of astronomers looking at Saturn and seeing a dramatically different planet, devoid of the iconic rings we know today. Saturn's rings are a reminder of the universe's fleeting beauty and endless mysteries. They symbolize how much we have yet to learn about planetary systems and the forces that shape them. With every new observation and mission, such as the groundbreaking data collected by the Cassini spacecraft, we edge closer to understanding their true nature. As we leave behind the splendor of Saturn's rings, let us now turn our gaze to another cosmic curiosity, the peculiar axial tilts of planets and the secrets they hold about the dynamic histories of our celestial neighbors. Moving forward, let us delve into the intriguing question of what causes the axial tilts of planets. As we look across our solar system, it becomes apparent that each planet has a unique axial tilt, the angle at which its rotational axis is inclined relative to its orbital plane around the Sun. This tilt determines how a planet experiences seasons, day-night cycles, and even the distribution of sunlight across its surface, making it a crucial factor in shaping planetary climates. But what creates these varied tilts, and why do they matter? The Earth, for instance, has an axial tilt of about 23.5 degrees, which gives us the familiar cycle of seasons. Contrast this with Uranus, which is tilted at a staggering 98 degrees, essentially rolling on its side as it orbits the Sun. Mars has a tilt similar to Earth, while Venus spins on an almost upright axis, yet in the opposite direction. These differences beg the question, what forces are responsible for such diverse orientations? One leading theory involves ancient celestial collisions. Early in a planet's history, during the chaotic period of solar system formation, massive impacts with other planetary-sized objects could have knocked planets into their current orientations. Uranus, with its extreme tilt, is thought to have experienced a colossal collision that tipped it over, leaving its axis nearly perpendicular to its orbit. Even Earth's relatively moderate tilt might owe its origins to a giant impact, possibly the same event that formed the Moon billions of years ago. Another possible explanation lies in gravitational interactions with other celestial bodies. A planet's tilt could be influenced over time by the gravitational pull of nearby planets, moons, or even the Sun. These forces can create subtle but cumulative effects known as axial precession, where a planet's axis gradually wobbles like a spinning top. For example, Jupiter's immense gravity is believed to have played a role in stabilizing the axial tilt of Mars, which might otherwise have fluctuated dramatically over geological time. The axial tilt of a planet is not just a trivial characteristic, it profoundly impacts the planet's climate and habitability. A slight tilt, like that of Mercury, results in minimal seasonal changes, while a dramatic tilt, like Uranus, creates extreme seasonal variations where one pole experiences decades of continuous sunlight followed by decades of darkness. On Earth, our moderate tilt creates the balanced seasons that have been vital in sustaining diverse ecosystems. Understanding the axial tilts of planets provides insights into their dynamic histories and the forces that shaped their evolution. Future observations and simulations may reveal more about the violent impacts and intricate gravitational interactions that determine a planet's orientation. But for now, the varied tilts of our celestial neighbors remain a testament to the complexity and unpredictability of the cosmos. With the mysteries of planetary tilts explored, let us now steer our attention toward another giant in our solar system, Jupiter. Specifically, the question of what powers its iconic Great Red Spot and why this massive storm has endured for centuries. Now turning to the fascinating enigma of Jupiter's Great Red Spot, we are faced with one of the most enduring mysteries of our solar system. This colossal storm, larger than the entire Earth, has been raging for at least 350 years, possibly longer. But what powers this swirling tempest, and how has it managed to persist for so long in the tumultuous atmosphere of Jupiter? The Great Red Spot is essentially a gigantic anticyclonic storm, where winds blow in a counterclockwise direction. These winds can reach incredible speeds of up to 430 miles per hour, creating a vortex of chaos visible even through basic telescopes from Earth. Unlike storms on our planet, which are typically short-lived, the Great Red Spot has defied expectations by enduring for centuries. Scientists believe that part of its longevity can be attributed to Jupiter's lack of a solid surface. Without landmasses to disrupt or weaken its energy, the storm has been able to maintain its momentum, fueled by the massive amounts of heat and energy emitted from Jupiter's lower atmosphere. Additionally, Jupiter's atmosphere is made up mostly of hydrogen and helium, creating a unique environment where storms like the Great Red Spot are not just possible but actively sustained. The planet's rapid rotation, completing a full spin in just under 10 hours, also plays a crucial role. This rapid spin generates powerful jet streams that help confine the storm within a band of winds, preventing it from dissipating or moving away. But why has the Great Red Spot been shrinking in recent years? Observations show that it has been gradually contracting, and its shape has changed from an oval to more of a circular form. Some scientists suggest that the storm is losing energy due to interactions with smaller storms or turbulence in the surrounding atmosphere. Others hypothesize that changes in Jupiter's internal heat or cloud dynamics might be altering the storm's structure. Despite this shrinkage, it remains uncertain whether the Great Red Spot will completely fade away or stabilize at a smaller size. One of the most remarkable aspects of the Great Red Spot is its striking color. The reddish hues are thought to arise from complex chemical reactions between ultraviolet radiation from the Sun and chemicals in Jupiter's atmosphere, such as ammonia and acetylene. However, the exact composition of these chemicals and the processes that produce the vivid red tones remain open questions. The Great Red Spot is not just a storm. It is a window into the mysteries of Jupiter's atmosphere and a testament to the planet's dynamic and powerful weather systems. As we continue to study this swirling giant, we may uncover deeper insights into the forces that drive Jupiter's weather and, by extension, the mechanics of storms on other worlds. With our gaze fixed on Jupiter's untamed fury, let us venture further into the cosmos and explore a concept even more puzzling: the existence of cosmic strings and their potential role in shaping the universe. Now turning to the intriguing idea of cosmic strings, we step into the realm of theoretical physics to explore these hypothesized structures that could hold clues to the universe's earliest moments. Cosmic strings are thought to be incredibly thin, one-dimensional defects in the very fabric of space and time, potentially left over from the universe's rapid expansion shortly after the Big Bang. Imagine them as unimaginably long and narrow filaments, thinner than a proton but with a mass so immense that just 1 mile of cosmic string could outweigh the entire Earth. These extraordinary objects, if they exist, might stretch across the vastness of the universe, forming intricate networks and influencing everything around them with their intense gravitational pull. One of the main ideas behind the existence of cosmic strings comes from the concept of symmetry breaking in physics. Just as water freezes into ice when conditions change, scientists theorize that the early universe underwent a series of transitions as it cooled down from its highly energetic and chaotic state. During these transitions, pockets of space may have formed irregularly, leaving behind imperfections in the cosmic landscape. These imperfections are what we call cosmic strings. If cosmic strings do exist, they could have played a pivotal role in shaping the structure of the universe. Their immense gravitational influence might have helped pull matter together, creating the seeds from which galaxies, stars, and planets eventually formed. Some theorists even suggest that cosmic strings could act as conduits for energy, transferring it across vast distances and potentially leaving behind observable imprints in the cosmic microwave background, the faint afterglow of the Big Bang. Yet, despite their fascinating potential, cosmic strings remain purely theoretical. No direct evidence of their existence has been found, and detecting them poses immense challenges. Scientists have looked for telltale signs, such as gravitational lensing, where the light from distant objects bends around the intense gravitational pull of a cosmic string. They have also searched for patterns in the cosmic microwave background that could hint at their presence. So far, these searches have not yielded definitive results, leaving cosmic strings as tantalizing mysteries that continue to fuel speculation. The idea of cosmic strings pushes the boundaries of our understanding of the universe, challenging us to think beyond what we can directly observe. If they are ever discovered, they could revolutionize our knowledge of how the universe evolved and reveal deeper insights into the fundamental nature of reality itself. With the mystery of cosmic strings lingering in our minds, it is time to unravel another question that lies at the heart of cosmic beauty. Why do galaxies, including our own Milky Way, take on elegant spiral shapes? Now turning to the captivating question of why galaxies, including our own Milky Way, form such breathtaking spiral shapes, we move deeper into the enigma of cosmic beauty. Spiral galaxies, with their sweeping arms and symmetrical elegance, make up some of the most striking visuals in the universe. Yet, their formation and persistence remain one of the great puzzles of astrophysics. At the heart of this mystery lies the concept of density waves. Instead of thinking of the spiral arms as fixed trails of stars, scientists propose that these arms are more like traffic jams in space. Imagine cars on a busy highway. Individual cars come and go, but the traffic jam itself remains in place. Similarly, stars, gas, and dust move in and out of these spiral arms, which are thought to be regions of higher density within the galaxy's disk. These density waves are believed to be triggered by gravitational interactions, such as a nearby galaxy passing close or disturbances within the galactic core itself. As material in the galaxy moves through these denser regions, it slows down slightly, causing stars to cluster and gas to compress. This compression can spark the formation of new stars, which is why the spiral arms often shine so brightly with young blue stars. The hypnotic spiral pattern might be a natural result of these processes, organizing the chaos of countless stars into a form that appears almost deliberate in its elegance. But why do these patterns remain so consistent over billions of years? One fascinating theory suggests that spiral galaxies exist in a delicate balance between gravitational forces and the galaxy's rotation. The collective gravitational pull of the galaxy works like a cosmic glue, holding everything together while the rotation spreads material outward, creating the iconic spiral structure. This equilibrium allows the shape to endure, even as individual stars and gas clouds move in and out of the spiral arms over time. However, not all galaxies share this shape, which raises even more questions. Some galaxies are irregular, others elliptical, and yet the precise conditions that lead to the formation of spiral shapes remain unclear. Researchers continue to study how factors like a galaxy's mass, rotation speed, and interactions with other galaxies contribute to its final form. Observations from advanced telescopes and simulations on powerful computers are helping us unravel these complexities, but the full story remains elusive. The mystery of spiral galaxies is a reminder of the universe's balance between chaos and order. These graceful forms challenge us to understand the forces and processes that shape the cosmos, and with each new discovery, we take another step toward unlocking the secrets of galactic evolution. As we ponder the elegant spirals overhead, let us move on to yet another fascinating question. Can a star really transform into a planet? Moving forward, we arrive at the intriguing question, can a star really transform into a planet? To explore this, let us first understand the unique relationship between stars and planets in the grand hierarchy of the cosmos. Stars, as we know, are massive celestial objects powered by nuclear fusion, burning hydrogen in their cores to produce the light and energy we observe. Planets, on the other hand, are much smaller and lack the internal heat to sustain such reactions. However, the line separating these two categories is not as clear as it might seem. In fact, there exists a fascinating middle ground occupied by objects known as brown dwarfs. Brown dwarfs are often referred to as failed stars because while they form like stars by collapsing from clouds of gas and dust, they do not gather enough mass to ignite nuclear fusion in their cores. Without this fusion, brown dwarfs cannot shine as brightly as traditional stars and instead emit a faint reddish glow, cooling over time. What makes them so interesting is that their size and mass also place them perilously close to the upper threshold of what we consider gas giant planets like Jupiter. Some brown dwarfs are only slightly larger than the largest planets, blurring the distinction between what is defined as a star and a planet. But what about an actual transformation? Could a star ever evolve into something more like a planet? While the process is not a direct metamorphosis, there is a scenario where a star-like object could end up resembling a planet. Imagine a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. Over billions of years, this white dwarf could continue to cool until it becomes a black dwarf, an object so cold and dark that it barely emits any light. By this stage, it might have more in common with a planet than a star, essentially becoming a highly evolved remnant of its stellar origins. Another captivating possibility lies in binary star systems. If a white dwarf in such a system loses enough of its mass through gravitational interactions with a companion star, it could eventually shrink to a size comparable to a planet. Though it would still retain its stellar core structure, its appearance and characteristics might mimic those of a giant, rocky or icy planet orbiting its partner. This cosmic ambiguity challenges us to reconsider the definitions we use to categorize celestial bodies. The universe operates on a spectrum of possibilities rather than rigid labels, and objects like brown dwarfs or cooled stellar remnants remind us of this blurred reality. As our understanding of these phenomena deepens, we continue to unravel how stars and planets exist not just as distinct entities, but also as part of a continuum where the boundaries are anything but fixed. And with this glimpse into the fluidity of the cosmos, let us push onward to another celestial mystery, what is causing the unusual dimming of Boyajian star. Now turning to one of the most puzzling mysteries in modern astronomy, we arrive at Boyajian star, also known as Tabby star. This star, located about 1,500 light-years away in the constellation of Cygnus, has captivated scientists and stargazers alike with its inexplicable behavior. Unlike most stars which display relatively stable brightness, Boyajian star has been observed to dim in irregular and often significant ways with no clear pattern or explanation. At times, its brightness drops by up to 22%, a phenomenon that defies the typical expectations of stellar variability. So, what could possibly cause such bizarre dimming? One of the first hypotheses proposed was a massive cloud of comets or debris passing in front of the star. This idea suggested that a swarm of icy bodies orbiting the star might occasionally block its light, creating the dramatic dips in brightness. While this explanation seemed plausible at first, further observations failed to find strong supporting evidence, as no accompanying infrared radiation which would be expected from the dust was detected. Another possibility is that Boyajian star is surrounded by an unusually large and complex ring of dust and gas, perhaps left over from the formation of planets or other celestial activity. This material might intermittently obscure the star's light and produce the irregular dimming patterns. However, this theory also struggles to account for the scale and unpredictability of the observed phenomena. Of course, one of the most extraordinary explanations that captured public imagination involves the idea of alien megastructures. Some researchers have speculated that the dimming could be caused by a massive, artificial construct orbiting the star, such as a Dyson sphere, a theoretical energy-gathering structure built by an advanced civilization. While there is currently no direct evidence to support this hypothesis, it underscores just how little we truly understand about the universe and its potential for harboring intelligent life. To add to the enigma, long-term observations of Boyajian star suggest that its overall brightness appears to be slowly decreasing over decades, a trend that complicates the puzzle even further. Could this point to a natural but unidentified astrophysical process, or does it hint at something entirely beyond our comprehension? The mystery of Boyajian star reminds us that the cosmos is full of phenomena that challenge the boundaries of our knowledge. Each new observation brings us closer to uncovering the truth, yet also deepens the intrigue. What lies at the heart of this stellar enigma remains an open question, sparking curiosity and encouraging further exploration. With this tantalizing mystery in mind, let us now venture into the realm of free-floating celestial nomads as we uncover the secrets of rogue planets. As the next phase of the journey comes into view, we arrive at the fascinating topic of rogue planets. These are planets that have broken free from the gravitational embrace of a star and now drift alone through the vast emptiness of interstellar space. Unlike the familiar planets in our solar system that orbit the Sun in predictable paths, rogue planets are cosmic wanderers, untethered and adrift. What makes rogue planets so intriguing is not just their solitude but the sheer difficulty of detecting them. Without a star to illuminate their presence, these planets are shrouded in darkness, making them nearly invisible against the backdrop of space. Scientists rely on advanced techniques like gravitational microlensing, which occurs when the gravity of a rogue planet bends and magnifies the light of a distant star as it passes in front of it. Even then, spotting these elusive objects is incredibly rare. The questions surrounding how rogue planets form and survive are just as compelling as their detection. Could they have been ejected from their original star systems due to violent gravitational interactions, or did they somehow form independently in isolation? If they were expelled, what kind of cosmic chaos could force a planet to be cast out into the abyss? Additionally, how do these planets endure the extreme cold and darkness of interstellar space without a star to provide heat and energy? Some theories suggest that rogue planets with thick atmospheres or internal heat sources might still sustain certain forms of geological activity or even liquid water beneath their icy surfaces. If so, could rogue planets harbor unique, hidden ecosystems protected from the harshness of space by miles of insulating material? The very existence of rogue planets challenges our traditional understanding of planetary systems, raising countless questions about their origins, frequency, and potential for supporting life. Each discovery of one of these wanderers is a reminder of the untamed and unpredictable nature of the cosmos. And as we continue to refine our methods for finding them, who knows what secrets these lonely travelers might reveal about the universe at large? With the mysteries of rogue planets swirling in our minds, let us now turn our gaze to the distant ice giants of our solar system as we explore what mysteries lie hidden within Uranus and Neptune. Now turning to the enigmatic ice giants of our solar system, Uranus and Neptune, we find ourselves faced with a wealth of mysteries hidden beneath their icy blue exteriors. These massive planets, located on the outer edges of our solar system, have intrigued scientists for decades with their unique characteristics. Despite being over 4 times the diameter of Earth, much about their internal structure remains unknown. What we do know is that they are fundamentally different from the gas giants Jupiter and Saturn. While the gas giants are composed mostly of hydrogen and helium, Uranus and Neptune are made predominantly of heavier elements like water, ammonia, and methane, a combination often referred to as ices in the context of planetary science. Yet, it is precisely what lies deep within these planets that continues to baffle researchers. Their interiors are thought to consist of dense, slushy layers of water, ammonia, and methane that are subjected to immense pressure and heat, potentially forming exotic materials like superionic water, a strange state where water behaves both like a liquid and a solid, conducting electricity. Could there be oceans of such exotic materials beneath their thick atmospheres? And what about their cores? Are they rocky, metallic, or something we have yet to encounter? These are the kinds of questions that remain unanswered because no spacecraft has ever directly probed the interiors of Uranus or Neptune. The Voyager 2 mission provided us with our only close-up look more than 3 decades ago, and since then, much of our information comes from telescopic observations and computer modeling. Adding to the intrigue, both Uranus and Neptune possess powerful magnetic fields that are oddly tilted and offset from their rotational axes. These unusual magnetic fields suggest something complex is happening inside these planets, possibly involving dynamic flows of conductive materials in their interiors. Furthermore, their atmospheres are dominated by some of the fastest winds in the solar system, reaching speeds of up to 1,200 miles per hour on Neptune. How these winds form and sustain themselves under such cold conditions is another puzzle waiting to be solved. Upcoming missions could finally shed light on these mysteries. Scientists are proposing ambitious spacecraft concepts to study Uranus and Neptune more closely, equipped with advanced instruments capable of analyzing their atmospheres, magnetic fields, and potentially even their internal structures. These missions could provide groundbreaking insights, not just into the ice giants themselves, but also into the many similar planets discovered orbiting stars in other solar systems. With so many questions about Uranus and Neptune still unanswered, the ice giants stand as a reminder of just how much we have yet to learn about the planets in our own cosmic backyard. And as we ponder the mysteries of these distant worlds, we turn our attention to a force that binds the universe itself, the elusive and perplexing nature of gravity. Now turning to the profound force that shapes our universe, gravity, we encounter one of the most fundamental forces of nature, and yet, intriguingly, one of the least understood. Gravity is the invisible force that holds planets in orbit around stars, binds galaxies together, and even shapes the very fabric of space and time. Described by Isaac Newton as the force that pulls objects toward one another, and later redefined by Albert Einstein as the curvature of space-time caused by mass, gravity has become a cornerstone of modern physics. But for all its apparent simplicity, gravity remains an enigma in many ways. Despite being the weakest of the four fundamental forces, which include electromagnetism, the strong nuclear force, and the weak nuclear force, it exerts influence over the largest structures in the universe, from planets and solar systems to galaxies and beyond. At the heart of the mystery is the challenge of reconciling gravity with the strange and counterintuitive principles of quantum mechanics, the branch of physics that governs the behavior of the very small, particles smaller than atoms. While Einstein's theory of general relativity provides an elegant explanation for gravity on large scales, such as the motion of planets and the bending of light near massive objects, it completely breaks down when applied to the extraordinarily tiny scales of quantum physics. For decades, scientists have been trying to develop a unified theory that merges general relativity and quantum mechanics, often referred to as the theory of everything, but the path forward remains elusive. Does gravity emerge from the quantum level in some way we have yet to comprehend? Could it involve undiscovered particles or dimensions that exist beyond our current understanding of the universe? These are the questions at the cutting edge of modern physics. Adding to the puzzle is the phenomenon of gravitational waves, ripples in space-time itself that were first predicted by Einstein over a century ago and only recently detected for the first time in 2015. When two massive objects like black holes collide, they send out these waves which travel across the cosmos, stretching and compressing space as they pass. The detection of gravitational waves has opened an entirely new way of observing the universe, allowing scientists to study events that were previously invisible, like black hole mergers occurring billions of light years away. But while we now have the tools to detect these waves, the exact mechanisms behind their formation and propagation remain an area of active research. Even closer to home, the nature of gravity raises questions about its role in phenomena we can observe but not fully explain, such as the way galaxies rotate. The speed at which stars orbit the centers of galaxies suggests there is much more mass present than we can actually see, a mystery that has given rise to the concept of dark matter, an invisible substance that interacts with gravity but remains undetected through any other means. Could understanding gravity more deeply finally unlock the secrets of this unseen matter, or might it reveal entirely new laws of physics? These unanswered questions demonstrate that gravity is not just a force we experience every day, but a profound cosmic mystery that challenges the very limits of human knowledge. With gravity's mysteries still pulling at the edges of our understanding, we continue to explore this force that binds the universe in ways seen and unseen. And as we leave behind the perplexities of gravity, we turn our focus to another groundbreaking discovery, the ripples of space-time known as gravitational waves. Now turning to the remarkable phenomenon of gravitational waves, we dive into a realm of cosmic ripples that have transformed our understanding of the universe. First predicted by Albert Einstein more than 100 years ago, gravitational waves are disturbances in the fabric of space-time itself, caused by some of the most massive and violent events in the cosmos. Imagine two black holes spiraling toward each other, colliding with such immense energy that they send ripples across space-time, much like how a pebble dropped in a pond creates waves on the water's surface. These waves travel outward at the speed of light, carrying with them information about their dramatic origins and the nature of gravity itself. It wasn't until 2015 that scientists confirmed their existence, using highly sensitive instruments capable of detecting distortions in space-time as small as a fraction of the width of an atom. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made this groundbreaking discovery when it observed the faint signals of gravitational waves produced by two black holes merging more than 1 billion light-years away. This moment marked the birth of a new way to observe the universe, not through light, radio waves, or particles, but by listening to the very vibrations of space and time. But detecting gravitational waves is no small feat. The signals are incredibly faint by the time they reach Earth, requiring instruments so precise that they can measure changes in distance as tiny as 1/10,000th the diameter of a proton. This sensitivity makes the study of gravitational waves one of the most challenging yet rewarding frontiers in modern astrophysics. Each detection provides a wealth of new data, allowing scientists to explore phenomena that were previously invisible, such as the mergers of black holes, neutron stars colliding, and possibly even fundamental processes that occurred in the earliest moments of the universe. What makes gravitational waves even more intriguing is their potential to unlock mysteries that remain hidden through traditional methods of observation. For instance, they offer a unique window into the nature of black holes, objects so dense that not even light can escape their grasp. By studying the gravitational waves emitted during black hole mergers, researchers hope to answer lingering questions about these enigmatic objects. Could gravitational waves also help us discover new laws of physics or detect phenomena we have yet to imagine? The possibilities are as vast as the cosmos itself. As we continue to refine our ability to detect and analyze these ripples in space-time, gravitational waves promise to reveal secrets of the universe that have been locked away for billions of years. They remind us that the universe is far more dynamic and interconnected than we ever imagined, a place where even space and time can ripple and dance under the influence of cosmic forces. And so, the study of gravitational waves not only deepens our knowledge of the universe, but also expands the horizons of human curiosity and discovery. With the next phase of the journey in sight, let us consider how these unanswered questions about the universe have shaped the very foundation of astronomy and space exploration. These mysteries, far from being mere puzzles, act as powerful catalysts that push the boundaries of human ingenuity and scientific progress. Take, for example, the quest to understand the nature of dark matter and dark energy. These elusive substances, which together make up most of the universe, have inspired the development of advanced telescopes, detectors, and computational tools, each designed to probe deeper into the cosmos than ever before. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope exist because of humanity's relentless desire to seek answers to space's most profound enigmas. Moreover, these unresolved questions fuel collaboration on an unprecedented scale, uniting scientists, engineers, and thinkers around the globe in a shared mission. The search for extraterrestrial life urges us to explore distant planets and moons, leading to groundbreaking missions such as the Mars rovers and the Europa Clipper, which aim to uncover signs of habitability beyond Earth. Even concepts like faster-than-light travel, though purely theoretical for now, have prompted innovative studies into the very fabric of space-time, challenging our understanding of physics and opening up possibilities we once deemed unimaginable. Unanswered questions also ignite a unique sense of wonder, inspiring the next generation of scientists, astronauts, and dreamers. The mysteries of black holes, neutron stars, and gravitational waves captivate the public imagination, driving support for programs that aim to unravel these phenomena. Educational initiatives, documentaries, and outreach efforts ensure that curiosity about the cosmos transcends academic circles, reaching people of all ages and backgrounds. It is this global fascination with the unknown that not only sustains funding for ambitious space projects, but also keeps the human spirit of exploration alive. As we build ever more sophisticated tools to study the universe, from particle colliders to interstellar probes, these unanswered questions continue to spark groundbreaking discoveries. Each step forward reveals new layers of the cosmic puzzle, reminding us that the pursuit of knowledge is a journey without a final destination. What we uncover along the way, be it the origins of the universe, the potential for life elsewhere, or entirely new laws of physics, enriches our understanding of existence and redefines our place in the cosmos. And as we move forward, these mysteries ensure that the spirit of discovery remains at the heart of human progress. With the next phase of the journey in sight, let us turn our gaze toward the future and consider how the mysteries of space might eventually find their answers. Advanced space missions and groundbreaking technologies on the horizon give us a glimpse of the possibilities. Imagine next-generation telescopes with the capability to peer deeper into the universe than ever before, perhaps even capturing the faintest whispers of the cosmos' origins. Missions like the James Webb Space Telescope, which is designed to study the first galaxies and the atmospheres of distant planets, could provide critical clues about the birth of stars, the nature of dark matter, or even the conditions needed to support life. Meanwhile, concepts like the extremely large telescope under construction in Chile aim to bring us closer to directly imaging alien worlds, studying their compositions, and searching for biosignatures that might indicate life's presence beyond Earth. Interstellar probes also represent a bold step toward unraveling space's greatest enigmas. The prospect of sending spacecraft beyond our solar system, equipped with unprecedented sensors and artificial intelligence, raises the possibility of mapping unexplored regions of our galaxy. These probes could examine rogue planets, delve into the mysteries of the interstellar medium, or even provide new insights into the structure of the universe itself. Additionally, the potential for quantum technology to revolutionize communication and data analysis could allow us to overcome current limitations, enabling real-time transmission from distant reaches of space and more precise measurements of cosmic phenomena. Closer to home, the planned lunar and Martian bases could play a pivotal role in answering long-standing questions about planetary formation and habitability. The Artemis program, for example, aims to establish a human presence on the Moon, opening the door for discoveries about its enigmatic history and how it came to be an essential companion to Earth. Similarly, Mars missions like Perseverance and future sample return efforts could deepen our understanding of the red planet's past, including whether life ever arose there and what it might teach us about life's potential across the cosmos. Efforts to investigate strange phenomena like fast radio bursts, neutron stars, and gravitational waves will also gain momentum with the advent of more sensitive detectors. Facilities like the Laser Interferometer Gravitational Wave Observatory, which first detected gravitational waves in 2015, are expected to evolve significantly, providing us with a clearer picture of the most extreme events in the universe. Imagine not just detecting the collision of black holes, but also understanding what lies beyond event horizons, or whether the ripples of space-time they create hold the key to a deeper theory of physics. Futuristic concepts such as harnessing antimatter, building warp drives, or creating energy-efficient propulsion systems remain speculative, but are no longer confined to the realm of science fiction. These theoretical developments continue to inspire scientists to explore the boundaries of what is physically possible, challenging established norms and encouraging the pursuit of truly audacious goals. As we advance, even questions that appear unsolvable today might eventually succumb to human ingenuity and determination, pushing the horizon of discovery further than we ever imagined. In contemplating the future, one thing becomes clear. While each new discovery will undoubtedly answer some of our most pressing questions, it will also spark new ones. The universe's infinite complexity ensures that there will always be mysteries waiting to be unraveled. This cycle of discovery and curiosity is what drives humanity forward, keeping our sense of wonder alive and reminding us that the journey of exploration is as boundless as the cosmos itself. As we bring this cosmic journey to a close, let us take a moment to reflect on the 30 unanswered questions that continue to baffle and inspire us. From the origins of the universe to the perplexing nature of dark matter and dark energy, from the enigmas of black holes to the tantalizing possibility of life beyond Earth, these mysteries remind us of how much we have yet to uncover. Each question challenges our understanding and pushes the boundaries of human knowledge, urging us to ask more, to explore further, and to never stop seeking answers. They are not just scientific puzzles, they are a testament to our curiosity and the unyielding drive to understand our place in the cosmos. But perhaps the most profound truth of all is this: for every answer we find, a dozen new questions will emerge. The universe is vast, its secrets infinite, and our journey through it will always be one of endless discovery. So as you look up at the night sky, let these mysteries spark your imagination. What do you think lies beyond the edge of the universe or inside a black hole? Could we ever unravel the true nature of gravity, or are some answers forever beyond our reach? We'd love to hear your thoughts. Which of these questions fascinates you the most, or do you have a theory of your own about one of these cosmic riddles? Let us know in the comments below. And if you enjoyed this exploration of the unknown, don't forget to like the video, hit subscribe, and turn on notifications so you never miss our next adventure into the wonders of space. Thank you for joining us on this journey, and remember, the cosmos